In this example, we're going to decompose the force into two component vectors, if you will. So in this example, we've got two ropes that are holding up a star, a holiday decoration. The star weighs 50 newtons, so that's a force. The ropes are fastened at different heights, and they make at different angles with the horizontal. One of them has 52 degrees, and one has 40 degrees. This one asks us to find the components of the forces for each wire, and then find the tension in each wire. Alright, so the first thing, let's just assume that we've got this in a two-dimensional plane here. So let's say it's the YZ plane, just by the way this is pictured. You can imagine it being in the XY plane. It really does not matter. We're just going to make it in the plane. Alright, we're up at the origin right here at the top of the star. Okay. So if we're going to have a vector that's in the direction of the forces in the shorter wire going this way, okay, it's going to need to counteract the weight of the star. So it's going to have to go up this way. One vector that's in that direction would be the length of that wire, and then we would do the cosine of 128 degrees, because that's this way, right? Because again, we're thinking about the axes being like so, right? This is the y-axis, this will be the z-axis. So going this way would be 128 degrees, because we know that this angle would be 52. So it would be 3 times the cosine of 128, and then the sine of 128 for the second coordinate. Mainly, this looks like polar coordinates, right? Okay. So we would have negative 1.847 and 2.364 approximately for those components. Do the exact same thing for the other wire. This angle here would be 40 now if we're imagining the axis going horizontally again. So we would have 5 is the length of the wire, cosine of 40 degrees times and sine of 40 degrees for our x and y components. And again, this looks a lot like polar coordinate ideas. Polar coordinate conversions, perhaps, maybe is a better way to say it. And we get 3.83 and 3.214 as our components of that one. All right, so those are just vectors that are in those directions. We really need to convert this over to make sure we hold up the same weight. All right, so the weight of the star is 50 newtons, but it's going to be pointing downward. All right, so the vector weight representing the weight of the star will be 0, negative 50. The other two weights, the F1 and the F2, that are going in the directions of the wires, have to counteract that force. So we need those two things to add up together to be 0, 50. All right, the vector that we found previously, the F1 vector, has to be parallel to that thing we found, so it has to be a constant times that. Likewise, same thing, a constant times the second vector we found, because it's going to have to be parallel to F2. So we got this vector equation to solve, or better yet, multiplying through our constants and equating components, we get a system of linear equations to solve. Choose whatever method you want, whatever your favorite method is for solving a system of linear equations, and you'll get C1 is 12.775, and C2 is 6.161. So now we've got what our first force has to be and what our second force has to be, just by multiplying those two constants that we found through. And that gives us our counteracting, if you will, of our force 1 and our force 2. Or, excuse me, counteracting our weight of the star using force 1 and force 2. The problem also asks us to figure out what the tensions in the wires are. Tension is just the magnitude of the forces. So finding the magnitude of each of these, you'll see that the tension in the first wire is a little over 38 newtons, and the second wire, it's going to be a little under 31 newtons.